Hello, Bioscience 101. This is Dr. Georgie, and we're now up to Lecture 10, Filter Selection. So if you have the Davidson-Murphy book, these are the pages where this material is explained. And let's talk about filters. So as you know, the filter cube in a fluorescence microscope has three components for each fluorophore. So there's an excitation filter, an emission filter, and a dichromatic mirror, also called a beam splitter, also called a dichroic, also, well, that's about it, three names. So these three components, two filters and one mirror, need to be aligned to whatever fluorophore it is that you're trying to image. So on a fluorescence scope, you're going to have as many filter cubes as possible. In truth, 3 covers most things. It covers, we only have 400 to 700 nanometers of light to cover. So you can design a scope. Typically, you start with 3, you go up to 6 filter cubes, and you usually can see most of the fluorophores that you're going to come across in a biology lab or a biotech lab or biomedical lab or a clinical lab. So let's look at the filter cube a little more carefully. The excitation filter, as you know, it only transmits the excitation wavelength. So this is where you're turning white light into the color that you need to excite your fluorophore. The emission fluorophore is going to transmit only the light that is created from your fluorophore, so only the emission wavelengths. It's also known as the barrier filter, because you're blocking any other color light other than the light that you want to see. And we have some choices here when it comes to choosing which emission filter. You can choose a bandpass filter that only transmits certain wavelengths, or you can choose a long pass filter, which transmits everything after a certain wavelength. And then the dichromatic mirror, as you know, is also called a beam splitter or a dichroic mirror. It's going to reflect the excitation wavelengths and transmit the emission wavelengths. And so here's another drawing of a filter cube, the light path. This should be pretty much what you're used to seeing already from the last lectures. And I really urge you to study this by drawing it out for yourself, puzzling it out, making flashcards, looking it up online. Do whatever you can to just absorb this material, because this is very foundational. And if this makes sense to you and is sort of easy to follow, then you'll be in good shape. So you want to get to the place where you look at this and you go, oh yeah, cool. Oh, I got this. I totally understand. And I am trying to pause this recording, and there we go. Nope. Okay, we're going to take a quick pause. Okay, now that you've looked at this, maybe even had time to draw it, take notes as you're studying this, listening, watching, however you do it. Let's continue on talking about the filter sets. So usually you buy a set. You can buy individual filters, but it makes sense that you're just going to buy them as a set. And these days you just buy the whole filter cube itself and everything's installed. In the old days, when they were more expensive, you might have only a few holders and more sets, and you'd be screwing, literally they screw in and out of the filter cube. These days you have filter cubes set up on your scope and you just turn a wheel or something and you get a new filter set into place. You don't want dust or anything to get on them, of course, so you want to try and protect them. So I said that the emission filter can be band pass or long pass. And actually any filter can, but you'll see that it makes no sense to have anything but bandpass for excitation. So that decision's made for you. Of course, excitation is going to be bandpass. And then the emission filter usually is bandpass, to be honest. It's a little bit dimmer than the long pass filter because it collects less of the light. That should be a the light. But it's just better for multiplexing. This will make a lot of sense once we start looking at them. So this is sort of notes on, pros and cons. The long pass, why would you ever buy it? Well, it's cheaper actually, and it's brighter. So if dimness is an issue, as it often is, it's an option to consider. And you'll know it's long pass when you go up to the oculars and you're expecting green, but you see green, orange, and red in your specimen. Because remember, things are spectra. Like, in other words, your emission, that colors that are coming off of your fluorophore are going to be, you're going to think of them as like green or the peak emission color. But actually, there's different colors coming off, just probably less of the orange and red than there is of the green. If you have a band pass, you're automatically setting it up so you see only green. If you have a long pass, you're saying, I want to see anything past a certain wavelength. You're going to see all the colors past that. And so it's fun to actually experience that. Because when you come back to campus, make sure you notice that we have different scopes. That we have Leica entry-level fluorescent scopes that have a long pass on them, and you can take the same sample from our Olympuses, which have band pass for, I can't remember which colors, but you'll figure it out. You just sort of take the slide and go on one scope and go, oh, it's only emitting green. You go on the Leicas and, oh, it's emitting a lot of colors. So there's nothing like, seeing is believing. Listen to what I say, learn it, but always be skeptical of anything you hear, right? So until you've experienced it yourself. Now, remember that for fluorescence, where dimness is an issue frequently, you're probably, if it's a fluorescent scope, you're probably going to have a black and white camera because they're more sensitive. To have a color camera, you're throwing away a lot of the info coming at you. And so you want to keep all of that info. So you're going to use a black and white camera. So if you have a long pass, you're in your image, you're just going to see intensity. You're just going to see, oh yeah, there's a signal here, there's a signal here, there's a signal here. It won't be color coded anymore. You've lost that information. You just know where there is a signal and how bright it is or not. You have the color info by knowing the information about the filter set, basically. You're like, oh, it's green because my filter set had a barrier filter for these wavelengths. So that's what I'm looking at. And if it's long pass, you basically have so many colors. You're like, I don't know, it was everything past a certain, nanometer wavelength. So getting fancier, there's scopes that will have filter wheels. Here's an image of one. Instead of a filter cube, you have two separate wheels, each with their own filters on them. And then I think you have a third wheel for the mirrors in between. Well, it depends on how the light path is set up, but everything's on wheels basically. And this is done because it's way faster to spin a wheel a tiny bit in order to switch between filter sets and thus fluorophores than it is to move a whole filter cube in and out. And these wheels spin really, really fast. We're talking milliseconds. Difference between I'm looking at red, now I'm looking at green, now back at red, green, blue, in milliseconds. So these are used on scopes that are kitted out for live imaging. And you really can't convert a scope. Like, it's either got filter wheels, you sort of have, or it's got filter cubes because physically the scope is set up differently. So you sort of have to know ahead of time when you purchase the scope, are you going to do live quick imaging or, and if you didn't set up your scope that way. You have to go find somebody who has one and befriend them, basically. So in cells, there's signaling where calcium is released in bursts, like quick bursts inside of cells. And so we have fluorescent dyes that show us this. For instance, when your heart beats, every muscle, when it beats, there's a burst of calcium and it goes away, and you can watch cells doing their beating thing, muscle cells, or just lots and lots of cells. Actually use this for all sorts of purposes. And that was one of the early uses of these scopes. So a scope that is set up for live imaging that can change the filter cubes, well, filter sets really fast by not having a cube. And you can also end up with more options. There's a danger here because you look at that little set of two wheels up there, you can easily make a mistake and pair the wrong set of filters together. So instead of having the, emission filter and excitation filter that you want, you can end up with something completely crazy. And because usually you can key in any combo that you want. These wheels are motorized or computer controlled, as are any cubes on motorized scopes. And like I said, this is a setup decision for the scope. So when you approach a new scope, if you don't know what it's got, you have to sort of just look at the software and poke around, look at the scope and figure out what's going on. So here is how we describe a filter set. Here is the information for each filter set is going to have its own diagram like this. And no surprise, on the y-axis, so on the bottom there, we're going to have the colors of light. So the wavelengths of light. In this case, this description goes all the way from 300 to 700. Sometimes it's 400 to 700. Look carefully, because they sort of don't make a big deal out of it. They being the people who are selling you these filter sets or describing them or whatever. When you look up a particular filter set, you gotta look carefully and see, what does my x-axis say? What am I looking at here? There's two companies, Omega and Chroma, that sell these to microscopists. And they're both wonderful companies with good products. And then on the other axis, the y-axis, you have how much of the light of that color is transmitted. So percent transmittance. This is a feature you're just stuck with, and pretty much most of the filter sets are around 80-ish or so, any good filter set. And it's just good for you to know that you're not actually, nothing's 100%. This is not, I don't know what. It's not heaven. This is real life. So nothing's ever perfect, but notice that you're throwing away light, like you're throwing away light because you're sometimes not catching the peak of what the fluorophore would prefer. And then you're throwing away light because you're only, 80% of what the lamp produces and so on. So at every step involved, there's some trade-off happening, some loss really happening. And, getting to the perfect system hasn't happened yet. And probably won't ever, because again, this is real life. This is good to know, to analyze your data, to understand it, to know why things are very different from one scope to another, where you might be able to not see something on one scope and then see it on another because it's set up differently. It's really important once you start trying to do quantitative microscopy, where you're trying to analyze the amount of signal you're getting, not just, is there a signal? Is it in the nucleus? Is it in these cells? Is it, in this part of the tissue or that part of the tissue? Or is it even there? I'm looking for, let's say, stain for COVID virus with, SARS-CoV-2 with fluorescence, is it there or is it not there? So you can ask all sorts of different questions using fluorescence, but usually you're just saying, like, does it exist? And if so, where is it? And if you're trying to do quantitation, which is absolutely possible, you're trying to say, how much do I have? How much of that particular protein or virus or bacteria do I have in this sample? Um, then we get into some really important quality control around knowing what your scope is, knowing what your filter sets are, or filter cubes, knowing the metadata from how you acquired it, knowing the specs of your camera. And a lot of people, I will say, you will even see published papers. A lot of people kind of avoid this and just go, it was brighter. and, and those of us in microscopy who are paying attention are actually trying to come up with some standards around reporting out, because not enough data is reported out about scopes currently on research papers and things like that. And it was brighter is meaningless unless you give us more info, because it was brighter could just mean you left the shutter open for longer, it was a longer exposure, or you had a filter cube that had a higher level of transmittance. Okay, so coming back to what are you looking at here? You're looking at a description of the excitation filter. You can see that. So the excitation filter in this particular case is going to only transmit light from 300 to 400 nanometers. And then you're looking at the barrier filter or the emission filter, which is going to transmit light beyond that up to about 550, looking at this. And there's always a third line for the dichromatic mirror or the dichroic or the beam splitter. And the mirror is, let me see if I think I have that on the other slide, but the mirror is basically going to mirror the emission filter too, right? Because whatever the emission filter lets out, the mirror lets out. And the mirror blocks the excitation colors, right? It reflects them. So when you look at what gets transmitted through the mirror, it's going to match your barrier filter in terms of the wavelengths. I hope you can see that on this. And so let's look at just another way of describing this. I mean, it's the same, it's just different colors. It's the same info for a different filter set. The red line is the excitation filter. The white line beyond it is the emission filter. And then the mirror is the yellow one that's going all crazy. And I make a point of showing you this representation of a filter set because don't get distracted by what the mirror is doing before the actual color of excitation. So before the color of excitation that you've got here is from 450 to maybe 500. You'll notice that, they could put more detail in these graphs, but next week for lab, you're going to go into the websites of these companies and you'll see they give you the exact wavelengths when you look up a filter set. So let's say that our excitation colors are 450 to 500, for instance. You want the mirror to go down to zero transmittance because it's reflecting those colors. It's sending them down to the slide, down to your specimen so that you get the fluorescence. And then again, once we get to whatever it is, 500, let's say the barrier filter is 500 to 560, let's just say something like that. You want your mirror to of course match it and to transmit whatever the barrier filter is transmitting. And then beyond what the barrier filter is doing, it doesn't matter actually, because you're only going to see what the barrier filter lets pass. Now, what about before, going back to that weird, crazy set of yellow lines before 450, over here, before 450, it doesn't matter. It's just the nature of how they make the mirrors and what works. We don't care what's happening from 350 to 450. The mirror is never going to get to see or experience that light, right? Because you're only shining light from 450 to 500, let's say, at it. And then your specimen, so that's you with the light source that you've provided. And because the white light first goes through the excitation filter. And so by the time it reaches the mirror, it's only whatever the excitation filter transmitted. So that's the only light that's going to come at it from the light source. And then, of course, you've got the light coming at it from your specimen, which it's going to let through. And, the barrier filter is going to block some of that and only let through some of it. All right, so let's look at bandpass filters. So bandpass filters have a beginning and an end to what light they transmit. And so they have two numbers basically, right? They have we'll let light through from here to here. And anything else they're blocking. You can have a narrow bandpass filter or a wide bandpass filter or kind of in the middle. These are just loose terms. Narrow this is from the Davidson website. It's a bit exaggerated because it looks like that narrow one is 5 nanometers or something. Usually even the best narrow ones are like 20 to 40 nanometers of light of wherever on the spectrum you're choosing to transmit it. And wide ones can be like 100 or 50 or more than that. Again, it's a loose designation just to sort of in your notes be like, this is a wide band pass, this is a narrow band pass. But somewhere in your notebook, you want to know the exact numbers of that particular filter. And if we're talking about a long pass filter, then it just means that there's only one number and everything it's very binary. It's like everything before or after is separated. So let's look at the middle one, for instance. Everything before, let's just make up a number, 500 is blocked, and everything after 500, actually they're showing you color. So it's a blue. So let's say it's 450 on that case. Everything after 450 is let through. Your dichromatic beam splitter in this case, they were like, I'm not choosing which name, I'm putting both names on there, is going to be a long pass because there's no reason it can't be. It just works fine if you think about it to have it be a long pass. But your barrier filter needs usually to be some sort of band pass filter, but sometimes, long pass filter is what you want. And so the options are there. And we don't really deal with short pass filters. That's an old thing that nobody needs anymore. So let's look at some fluorescence filter sets, or its fancier full name, epifluorescence filter sets. Again, people just use whatever they feel like using. Formal name, shorter name, fluorescence, full name, epifluorescence. Epifluorescence is what you'll see in papers, for instance. So scientists tend to have lab jargon, the way they actually speak, and they will use that in talks too. And then when they sit down to write these lab reports that are papers that are published forevermore, then they'll pull out the formal official actual name. So that's, you'll see epifluorescence in writing, and then people just say fluorescence in real life. Okay, so here is just the fluorophore of, in this case, FITSI. So it's got an excitation spectra and it's got an emission spectra. You're totally used to this. This is old hat, old news. Now we're going to add some more info because we're going to draw on the same exact graph. We're going to draw the filter set for this fluorophore. And this is the kind of thing that you want to get used to looking at in an instant. You just kind of go, yeah, that's a good one. No, that's a bad one. So there's a lot of beauty and a lot of info in this graphic here. And you want to, like I said, you want to just look at these, and next week I'm going to have you draw some so that it's going to make a lot of sense to you. You want to be really comfortable with these. So you already know what the fluorophore is. And if you'll notice, the x-axis, the bottom there, is it's nanometers for both of these charts. This is again 2 charts on top of each other. Just like when we were looking at the histogram and the lookup table, is actually 2 charts right on top of each other, because it's way more useful to put them on top of each other than to have them separate and try to guess, like, does that align? Just the way our eyes and brains work, let's just put them on top of each other. Okay, so in both cases, they're gonna have, as the x-axis, it's the colors of light, visible light. Okay, that's easy. What about the y-axis? Well, actually, it's the same story. On the y-axis, it's how much light gets, well, actually, I should say the filter set selection is what's noted there, which is how much light is transmitted. In the case of the spectra, it's sort of the same thing, because we're talking about how much light is there. And, you know, in emission, it's how much light is created, and excitation is its response to that light. But it's basically, you know, how strong, how much light. And we sort of don't deal with the y-axis a lot because there's not a lot you can do about it, to be honest. But we look at very carefully at the axis at the colors. And so you can see in this case with FITSI, the filter set that we're choosing, look at the blue line for the filter sets. It's almost 80%, maybe it's 70% transmission. But the important thing here is the colors. The colors are 450 to 500. That is barely catching the peak, which is 495, I think, if I'm recalling correctly. So, okay, yeah, we're gonna excite it with the light it prefers mostly. We can't go really past that because the spectra, the emission spectra kind of overlaps. And then we're going to collect from, let's say 510 to 560. We're not quite collecting quite the brightest color, but we're close to it. So sometimes this is as good as you can get, and you've got to get a little separation between the excitation and emission filter. So this is a perfectly adequate filter set for FITSI. And it's a narrow bandpass, because look at both of those filters. I hope you can see why instinctively the excitation filter needs to be bandpass. You can't just give it all the light. You need to give it a certain color of light. And then with the emission, you can collect all the light if there's no other fluorophore around. Or in this case, you can collect not quite all of the light, all the possible colors that are going to come off of this fluorophore, off of your specimen, but you're collecting most of them. And the colors you're missing are really dim anyway. So, you know, you're doing a pretty good job by our standards. This is a decent filter set. Nothing wrong with it. It's pretty average. And the emission is a narrow band pass. And then, of course, there's our mirror, which always has just a fun little, you know, shape to it. I think you know, it's doing its little crazy dance in front of the colors, the you know, the 300 400 nanometer colors, whatever. It's just there to be amusing, honestly. What we really care about is, does it, here, let's look at this, does it fully block, in other words, does it not transmit the colors of the excitation filter? Okay, so when the excitation filter goes up, the mirror goes down. And then the emission filter goes up, the mirror goes up with it. And keeps going up afterwards, but whatever. Those colors aren't relevant. They're not coming to our eyes or to our sensors on our cameras. Here's a wider band pass. So let's go back and forth and look at the red line, the emission filter, and you can see it's a band pass because there's only certain colors that it lets through. There's two colors, the one where you can it'll start transmitting, and the one where it stops transmitting. So you describe it with those two colors. And then look at it now, it's still a band pass, it's just a little bit fatter. So this is a wider bandpass. It's essentially the same filter set, just a bit fatter. So, you know, yeah, maybe we want this one if we're only using FTSE. This one will give you a brighter signal. That's the key thing to notice about it. Like, this is where, you know, you can look at the same specimen with this filter set, with the narrow bandpass filter set, and then with the wide bandpass filter set, you will get a brighter signal because you're collecting more of the colors and therefore more of the signal. Because remember, your specimen is emitting a variety of colors in response to the variety of colors you excited it with. So the emission spectra is what it is, and those are the possible colors, and you're guaranteed, no matter which of its chosen excitation colors you excite it with, you're going to see a range of colors as your emission colors. And you can collect all of those, or like in here, you can collect not quite all of those. But again, some of the colors more in the red are going to be very rare. You're not going to see a lot of those. So it's not like you're throwing a lot of info away with this narrow bandpass. But you know, this is preferable if possible. There's trade-offs again, because as you'll learn soon, if you use this narrow bandpass, you can also maybe squeeze in collecting different fluorophores. You can multiplex, you can collect some red. If you're just like, oh, the only thing I need to see in this specimen is FTSE, then go right ahead, have a nice wide bandpass. In fact, if you're sure that the only thing that you're looking for is your FTSE signal, then fine, go with a long pass. So do you see how this one only has a number? It's like after, you know, 502 and on, everything can get transmitted, go up to people's eyes or to the camera. We're going to collect all of that as data, any color. Now, it would let, you know, 670, 700 nanometer light through, but there isn't going to be any coming from your specimen, because your specimen is only going to fluoresce and give you light up to 650 according to the spectra of the fluorophore. But your bandpass is going to take all the light. So is this going to be brighter? Yes, this is the brightest of all those three filter sets. They're all for FTSE. You're looking at the same thing, at the same specimen, the same fluorophore, and you can try these three different filter sets, and each one will be, you know, this narrow bandpass will be great. This wide bandpass will be a little bit brighter, and this long pass will be even brighter. And if you looked at it in the oculars, you would be able to see the different colors. So which one is the right filter set to choose? None of them. There's no such thing. It just depends on your actual experiment, on on your experiment. What are you going to do? What are you trying to see? And if you don't know and you're trying to set up the scope, you go for the narrow bandpass and deal with the dimness. But you know, if you can buy all three of them, then buy all three of them. Although people don't do that. Usually you kind of know what you're studying when you set up a scope and you think about it ahead of time. But then you might change what you're studying, in which case you're like, let's order a new filter cube set. Fortunately, they're only about $300 or so, so it's doable in terms of the budgets of a lot of labs. Okay, so as I say that, I'm like, wow, it really depends on the lab. For some labs, like a commercial biotech or clinical lab, that's nothing. If you're in academia, it depends. Some labs have a lot of money, some labs, they're like, oh, no, $300? Are you kidding me? I'd be lucky to get a $5 part. And then you do what was famously done. Well, I'll tell you about this in the GFP lecture, but you sometimes can get scope reps to demo things sometimes. Although filter cubes, I don't know. There's always workarounds. There's always somebody who has what you need, and then you just befriend them. Okay, so let's look at another filter set. So this is for Alexa 488, so another green fluorophore. Here's just the fluorophore. Let's look at some filter sets. Here's bandpass. Again, kind of like before, we're doing a decent job of capturing, you know, the colors that this fluorophore prefers for excitation, and we're capturing most of the emission colors. And the mirror is just perfect as usual. Here's the same fluorophore, only a long pass. So as you can see, there's only one number for the emission filter, and the excitation filter always needs to be a band pass, because you're not going to excite it with all the colors. You're going to excite it with a particular color. And you can, however, capture all of the colors that come off of your specimen. Why not? If you can, do it. And if you can't, oh well. Here's GFP, so another green fluorophore. This is enhanced green fluorescent protein. And here's a nice narrow bandpass filter set that hopefully by now this is starting to be repetitive. You're, where's the excitement? The first one was really interesting. This looks just like the other ones. Well, yeah, that's the idea. They're all pretty similar. The excitation filter is going to follow your excitation spectra for the fluorophore, and the emission filter is going to follow the emission part of emission spectra for the fluorophore. So hopefully we're good at patterns. You're starting to decode the pattern here. There's like the light that the fluorophore wants. Oh, we're going to put the excitation filter right there. The light that it's creating that you want to see, that's your signal. Oh, we're going to put the emission filter there. And the mirror does its usual dance of just hanging out until it's called into duty, and there it is, dipping down and blocking all of the excitation light so that it goes down to the specimen, and then letting all of the emission light colors through so that the barrier filter can block them, and then you're going to only see certain colors. And here's a wider version of the same filter set. So this has a wide band pass. And then can you guess what I'm going to show you next? Oh, sorry, I faked you out there. I'm not going to show you a lot. I faked myself out that I had a long pass filter set for this, but you can imagine what it is. It's basically, it would be 500 onwards. Okay, let's look at some red fluorophores. So like all the way over in the 600s with the emission, the excitations in the 550s and so on. So what are we going to do with that? Well, once again, we're going to match the filter set to the spectra of the fluorophore. And you can look at this, and this is a good example of a combination where you're missing the peaks because you just have to, just the way the way this fluorophore is. So you're exciting it not quite with, well, you're giving it the color it prefers, but you're really not capturing the color that is mostly coming off of it, but you're making it up for it by using a nice fat band pass. Usually red is your last color, so you can have a band pass or a long pass on the red. And then the mirror, we're going to check, yeah, that looks like the right mirror for this set. Everything's good. Okay, let's look at another red, a Tritzy. You might be thinking, isn't red all the way to the end of our chart or our table? And look at what they did for no good reason down there with the numbers 350 to 900. 900, what? 900 is not visible light. Why are you showing me anything past 700? Well, because it's physics, people, and they're like, let me show you the cool stuff that happens at the light colors that you're never going to look at. So they're giving you the complete story here. This is a good example of look down at the actual numbers, not where, because if I just looked at this, I'd be like, oh, this must be green or even blue. It's kind of in the middle. No, it's not. It's red because it's in the 500s for excitation and in the 600s for emission. And it's, again, a long pass, as you can tell, I hope by now. And well, that is pretty much it. So I want you to look at these, get comfy with these. I might post your assignment spectra a little bit early if you want to get started on that. I've covered the information you need for the first two exercises and so far. And then the third exercise on your lab for next week, which will be spectra. That third exercise I'm going to cover next week. So just so you know, if you hit it and you're like, wait, what is this stuff? I haven't heard of it. That's because that's next week's lecture. So a little bit about beyond the cube, as I like to call it. So filter cubes are superb. They're so useful, so interesting, so wonderful, so important. They gave us fluorescence microscopy. We love filter sets and filter cubes and fluorophores and their spectra and matching them to the filter, you know, finding the fluorophore that the filter set that matches your fluorophore, or sometimes the fluorophore that matches your filter set. If you've already bought the scope, if it already exists, then you're like, well, what experiments can I do? Let me match it to my microscope. So about, I'm trying to remember when, about 10, 15 years ago, there were some innovations that came about that are known as spectral imaging. Now it's standard on any confocal microscope, basically. Just so you know, on the old confocals, you had a filter wheel usually, or filter sets. You still had filter sets for emission, at least, because you're usually using a laser. So that's actually just one color. It's not even a, a spectrum of colors. But you were still having this issue of what do I do about what I'm collecting, the light that I'm collecting. And then Zeiss and Leica almost simultaneously came up with what is called spectral imaging, where they allow you to basically create a emission filter custom on the spot in the moment. So when you're sitting at the scope, there isn't a physical piece of coated colored glass that you're putting in the light path like there is on, you know, regular fluorescent scopes, and there used to be on confocals. And there still is on older confocals that are still out and working. But there's a whole system of either prisms or diffraction grating physics and fun like that, physics and optics fun, where um, you can dial into the system which wavelengths you want to see. So I can just sit there and in an instant say, show me emissions from, you know, 550 to 562. Well, okay, that's what, okay, let's go to 570. Oh, no, okay, let's see what happens if I go to 580. Like, and in fact, they'll even draw the spectra of the fluorophore on there for you as a guide. So, you know, you can guess something useful. And it's really, really fun. It's really fun. Also, it's basically like you have all the filters ever invented, all the barrier filters anyway, ever invented at your fingertips at a moment's notice. And you can just dial in what it is you want to, what do you want to see? What colors do you want to see coming out of your system? Also, you can dial it down to 5 nanometers. So, which you can't do physically with actual glass. So I can say, I want to see everything from 550 to 555, and it can do that. And because it can do that, what I can also do is a cool thing where I go I want to see what's 550 to 555. Okay, give me the picture from 555 to 560. Okay, give me 560 to 565. You get the idea. You start stepping it along, and you're basically going to recreate that spectra that was given to you for the fluorophore. Or if you're using a fluorophore where you don't know what the spectra is, you can actually use the confocal to capture and know the spectra of what you're looking at. Very useful because things like pH will change how a fluorophore fluoresces and what their spectra is. And so there's all sorts of info. It's basically acting like a SPEC, a spectrophotometer, which is a machine used in chemistry and physics mostly to just look at it's to actually, that those spectra were created by putting the fluorophores into a tube and using a spec to measure the different colors that are coming off of something or that are present in something. So that's what a spectrophotometer does. And the confocals are basically a really expensive spectrophotometer. It costs a lot more than a normal spec, but that's because they're doing a lot of other things, but it's like a side job that they can do these days. And it's, when I wrote this, it was relatively new, but now it's pretty standard. It's not even highly mentioned in the salesperson's patter anymore. It's sort of like it's an expected thing. It's still a really wonderful part of a confocal. And I think that covers it for this week for lecture.